Let's pretend for a little while that you're going on a little treasure hunt. You pull out your treasure map. X marks the spot right here. But in order to figure out where this treasure is, you need to do a little navigation. So you pull out your compass as well. You put your compass on the side of the treasure map right here, and you find that it points this way, points toward the North Pole. We really know that's magnetic South Pole, right? But we usually call it the North Pole. And then it starts getting a little dark. So you got this lamp beside your treasure map here with a cord going across the table. Okay? You get the treasure map right on top of that cord, and the lamp is over here. You flip on the lamp, and all of a sudden, this compass that was pointing towards the North Pole, or magnetic South, starts pointing this way. What's going on? You flip off the light switch, and all of a sudden, the compass goes back to pointing this way. You flip it on, it goes to pointing the other way again. Okay, flip it off, and so on and so on. So then you start messing with the light. What's going on here? Why is this causing the compass needle to point in crazy directions? You discover it's not the light that's causing it to point in crazy directions. It's the presence or absence of electricity that's causing it to point in crazy directions. When I turn on the electricity, the compass needle points one way. When I turn off the electricity, it points the other way, the way that it's supposed to point, right? Magnetic South Pole, or what we think of as the North Pole. The conclusion that we draw from this is the same as the conclusion that a guy named Hans Christian Oersted almost 200 years ago drew from a similar observation. He wasn't looking for treasure, but he accidentally noticed that a compass needle was deflected in the presence of an electric current. In other words, the electric current must generate a magnetic field that kind of supersedes the Earth's magnetic field, stronger than the Earth's magnetic field, so it causes the compass to be deflected in a direction other than the natural North Pole or magnetic South Pole. Now, this phenomenon works not just with wires carrying an electric current, but anytime you've got moving charges. That's really what a current is, right? Moving charges. Whether it's inside a wire or just moving random ions through the air, as soon as you have moving charges, you've got a magnetic field generated. It's a predictable magnetic field. It's a predictable shape. It's a predictable direction. And we'll see in just a moment what that shape and direction is. Understand the importance of this, okay? This is, in my mind, one of the most important scientific and technological discoveries in the history of the world. Think about all of the things that we have today that are based on this discovery, that are based on this technology, the idea that electric currents generate magnetic fields. We have no cars as we know them, okay, if we don't have this technology. We have no computers, certainly. We have no speakers for our stereos. We have no stereos, let alone the speakers for our stereos. We have no phones. We have no iPhones. We have no home phones. We have no just about anything. Just about any of our toys that use electricity use this principle, that electricity generates magnetism. So what does the shape of that magnetic field look like? I told you it was a predictable magnetic field. What does the shape of that magnetic field look like? You guys will remember earlier on this year, we had to indicate, I can't remember the context of it actually, but we had to indicate a direction that was away from us or towards us. Remember we said that the X represents something going away from us, and a dot represents something coming towards us. Remember the story that I told you guys about getting the dart thrown on my back when I was a kid? Remember that one? Right? We picture the dart coming towards us. It looks like a dot. We picture the dart going away from us. It looks like essentially the X, right? We're going to say here right now that the X is representing not just anything going away from us. Could be a car going away from us. Could be a field line going away from us. In this case, it's going to represent a charged particle, a negatively charged particle going away from us. An electron going away from us. The magnetic field that surrounds that electron that's moving away from us, we could say into the page here, into the board, is always going to be the same shape. It's always going to be circular. Not just one circle. There's a series of concentric circles, meaning that it's one circle inside of another circle. Notice the proximity of the field lines. The further you get away from what's causing the field, the further apart they get, which means the further you get away from the wire that's causing it, the weaker the field strength is. And that should make sense to us, right? If you get further and further away from what's causing the field, that field is going to get weaker and weaker. But a magnetic field is a vector field, just like a gravitational field or an electric field is a vector field. So it has a direction associated with it. Here's what I want you to do right now to determine the direction of the the magnetic field. I want you to take your hands, drop your pens, take your hands. We're going to do a little rule that Oersted would have taught us here to find the direction of the field. Take your hands, put them up like this. Okay, I want you to stick your right hand in, your right hand out, your right hand in, and shake them all about. Do the, no, never mind. We're going to learn over the next several days 3 different rules, 3 different tools that you're going to use either a left hand or a right hand for that are going to enable us to determine various things. Today, we're going to learn the first of those rules. We call it the wire grasp rule. The wire grasp rule is a rule that allows us to find the direction of the magnetic field caused by moving charges. And here's how it works. You got a negative particle, left hand, positive particle, right hand. We got a negative particle in this case, I said, going into the board or away from you guys. So here's what I want you to do. I want you to stick your left thumb into the board. Stick your left thumb towards the front of the room. Everybody do this. Okay, you can watch me do this and say, oh, I get that. But you're not going to be able to do it yourself unless you actually do it. Okay, stick your left thumb towards the front of the room. Now make sure that your left thumb isn't like this, kind of clenched up. Make sure your left thumb is sticking out. Okay, like you're hitchhiking on the side of the highway. Except you're sticking it forwards this way. And make sure it's your thumb that you're sticking out, not some other finger that you're sticking out. Here's my left thumb. Now what I want to do is grasp the wire. Pretend there's a wire in your fingers. Grasp it. Now it doesn't matter how much you grasp it, whether you do this or whether you just do this. My suggestion is don't make it like, don't grasp it tightly. Just bend your fingers a bit like this. It is a little bit awkward, Wyatt, but if you try just doing this, it's not so awkward. Wait till we get to a couple of the other hand rules, and you start doing things like, why you're gonna have to start doing things like this, and then it gets really awkward. Your fingertips, your fingernails should point in the direction of the magnetic field. Now, some of you think, oh, okay, I get this. Okay, fingers point in the direction of the magnetic field, but some of you are looking around and saying, wait a second. Like my hand looks different than everybody else's hand. Okay, Wyatt has his hand like this, where the fingers are pointing kind of downwards like this, whereas somebody else has their hand like this, where my fingers are pointing towards the left. So which is it? Doesn't matter. Okay, the magnetic field here is to the left. The magnetic field here is down. The magnetic field here is to the right. The magnetic field here is upwards. So it doesn't matter where you put your hand. As long as you stick your thumb in the direction of the moving particle and you bend your fingers a bit, you'll see that the magnetic field here is counterclockwise around this. All right? If you bend your fingers even more than the person beside you, like this, bend them more. Well, it's a little bit harder to see then, but in the end, it's still, the fingers are still pointing counterclockwise there, right? So thumb, okay, stretched out, not against your fingers here. Thumb is stretched out. Thumb in the direction of the particle, which is toward the front of the room. Bend your fingers a bit. and it's going to go counterclockwise. Let's try another one. Let's try this time where the particle is coming towards us, okay, out of the page or out of the board. Now for you guys, if you were to draw this on your page, it's coming up, right? For me, it's coming from the front of the room. For me, I'll stick my thumb away from the front of the room. For you, you'd stick your thumb, if you're using your page as the frame of reference, you'd stick it up from the floor, right? Out of the page. I'm going to grasp the wire, bend my fingers a bit. Doesn't matter exactly how much. We're going to see that they're pointing clockwise, like this. Now, really, by rights, we should draw more field lines showing the spacing of them as well. But really what we're trying to accomplish here is the direction of the field, not so much the strength. All right. Let's try another one that's a little bit harder. Here we've got a wire, and it has an electric current going through it, and negative electric current, electrons going towards the right side of the page. I want to know what the direction of the magnetic field is above the wire, below the wire, in front of the wire, and in back of the wire. Okay, if this board marker is my wire, then we know it's going to be a circular field, right, around it. But which way is the field pointing at those 4 spots? Okay, it's the left-hand rule again, because it's a negative particle. If it was alpha particles or protons or something like that, it would be a right-hand rule. Left-hand rule, thumb in the direction of the particle. Remember to keep your thumb out like this. Direction of the particle towards the right side of the room. Now, I want you to look at me. Picture this as your page, okay? Now, from your frame of reference here, from your perspective, okay, right now my fingers are in front of the page, or in front of the wire. Make sense? If this is the page, okay, my fingers are, and this is the wire, my fingers are in front of the wire. That make sense? Not which way they're pointing. Where are they? Where are my fingertips right now? Okay, if this is the wire, and my fingers are between the wire and you, then my fingers are in front of the wire. Which way are they pointing when they're in front of the wire? Which way are my fingertips pointing now? Yes, up. And you say, well, wait a sec, now they're not pointing up. No, they're not, but they're also not in front of the wire right now, right? Now they're above the wire. So when they're in front of the wire, they're pointing up. But be careful. We don't want to say up here, because our frame of reference is the page. We want to say toward the top of the page. Why? Because look at my page. My page is vertical. Yours is horizontal. For me, towards the top of the page is up, right? Towards the ceiling. But for you, toward the top of your page is toward the front of the room. That make sense? For all of us, my fingers are pointing toward the top of the page. So let's use the page as a frame of reference there. Okay, let's do another one here. Now let's say it's behind. Okay, this is when it gets a little bit tricky. I could turn around, I suppose. It gets wacky even. Why it gets wacky even for me here still. Let's stick my thumb in the direction of the particle again, but let's stick my fingers behind the wire this time. Okay, you see they're behind the wire? Which way are they pointing? Which way are my fingers pointing right now? Down. We're going to say toward the bottom of the page, toward the bottom of the page, right? Okay, they're actually down here toward the ground, but if we're looking at your frame of reference, the horizontal page that you've got it drawn on, it would be toward the back of the room, right? Bottom line is it's toward the bottom of the page for all of us. So we're going to say toward the bottom of the page. Okay, right now my fingers are above the wire. Which way are they pointing? Well, you could look at the way that I have it expressed right now with my frame of reference and say it's toward the front of the room, right? But for you guys, picture this. Your fingers will be pointing into the page. You could simply draw it this way, into the page. And below the wire, they would be pointing, if this is the page, they'd be pointing out of the page. Represent that by a dot. How does this change if it's a positive particle? Well, we use our right hand, but that's it. Everything else is exactly the same. What I'd like you to do now is to take a look at worksheet number 10, please. Worksheet number 10. There's 6 questions on that worksheet. No mathematics. All 6 questions just ask me to do something similar to what I've done here, or here, or here. Take a look at that worksheet. I'll take a walk around. Stop me if you're having any trouble with it at all, and then once you're finished, we'll take a look at it as a group. Okay, let's take a look at these. Question number 1 and 2 are relatively straightforward. When we get into 3 and 4, that's when it becomes more challenging for us, okay? So we'll go over 1 and 2 pretty quickly here. We have a wire showing electron current into the page, represented by the X. We're going to say, we know it's a circular magnetic field. There's a bunch of circles, but if we draw one, that's okay. Thumb in the direction of the particle, fingers are going to go counterclockwise here. So it doesn't matter exactly where you find your fingers pointing, okay? If we twist them around, we're going to find that it points counterclockwise. So look at the next one. We have a wire showing electron current coming out of the page as represented by the dot. Now remember, your page is different than my page. My page is vertical, your page is horizontal. Our frame of reference is still the page. So for me, okay, the electron right now is moving towards the back of the room. For you, the electron coming out of the page is moving towards the ceiling. Okay, we're using the page as our frame of reference. For me, I would stick my left thumb out of the page toward the back of the room. For you, you would stick your left thumb out of your page toward the ceiling, right? It's out of the page, regardless of which way your page is oriented. So we do that. We're going to say thumb in the direction of the particle. Fingers are going to go, looks like the fingers are going to go clockwise this time, right? No matter where we have our fingertips, they're going to point clockwise. Now, this is where it starts getting tough for question 3 and question 4. We have electron current going to the right. That means that our left thumb would go towards the right of the page. Now, what people have trouble with in this one is not so much where to put your thumb, but how to put your fingers in front and behind the wire and so on. Here's what I suggest to those of you who asked questions as I was walking around. This is what I tried to get you to do. Take your pencil or your pen and make it your wire. Okay, we have that wire pointing towards the right side of your page. Okay, because remember, we don't want to say towards the right side of the room, right? Look, here's Ben's page right now. It's pointing towards the right side of the page, towards the right side of the room. But what happens when he flips his page around? It's still toward the right side of his page, but it's toward the left side of the room, right? So our frame of reference here is the page, unless we're given some other frame of reference. Here's what I want you to do. Take your pen or pencil and set it right above your page. Okay, this would be in front of the wire. This would be behind the wire. This would be above the wire. This would be behind the wire, or below the wire, I should say. Does that make sense? Now, for me, this would be in front, this would be behind, this would be above, this would be below, okay? But if the frame of reference is our page, okay, it doesn't really matter whether our page is vertical or horizontal. We still get the same answers. Okay, let's do it from your perspective here. Okay, here's my pen. Here's my wire going this way. Right now, my fingers are, take a look at where they are. They're in front of the wire. They're in front of the wire. And they're pointing, if this is my page, my fingers are pointing out of the page. So in front of the wire, we'd say it's out of the page. Now, right now, my fingers are behind the wire. Okay, see, this is the wire. Okay, this is the page. They're behind the wire. My fingers are pointing toward the bottom of the page. I don't want to say, like, towards me or towards you or towards the back of the room or towards the front of the room, because if you turn your page, then all bets are off, right? But if we say toward the bottom of the page, it doesn't matter how we have our page oriented. Horizontal, vertical, diagonal, turned around 180 degrees or what. So we're going to say behind the wire, it's toward the bottom of the page. In front of the wire, it's toward the top of the page. Below the wire, it's out of the page. And above the wire, it would be into the page. Number 4, find the direction of the magnetic field surrounding the moving alpha particle. This is probably something we want to draw attention to, right? The fact that it's an alpha particle, it's positive. We're going to use our right hand for this. Once you get the rules, once you understand the rules and are able to use them, the most common mistake by far that we find is that you use the wrong hand because you're just not paying attention. It's an alpha particle. Oh, left hand. Because habit, right? Because it's always a left-hand rule. It's not always a left-hand rule. Sometimes it's the right-hand rule. Here's my alpha particle. Okay, from your page, it looks like this. Right now, my right fingers are to the left of it. They point out of the page. When they're behind the wire, it's to the left of the page. When they're in front of the wire, okay, remember, this looks like it's above, but from your perspective, okay, from the perspective of your page, it's in front of the wire. Okay, here's the page. My fingers are in front of the wire, and they're pointing towards the right side of the page. And then to the right of the wire, they're pointing into the page. Sometimes a question like number 4 and 5, it's difficult to get when I'm standing up here doing it for you. Okay. Sometimes we need to actually, I need to physically take your hand and twist it around in various shapes so that it's pointing in right directions. Okay. Usually that works. So if you're having trouble with this at all, please let me know. Come in during scheduled help tomorrow or lunchtime tomorrow, and we can see what we can do to make sure that this works for you. Okay. Okay. Last question. Sorry, I meant question 3 or 4 if you're having trouble with either of those. Question 5 and 6, a bit different. This is kind of like algebra, kind of like when you started physics 20 or science 10. Started science 10, have to rearrange the equation V equals D over T, and you guys are all trying to use the stupid triangle thing to rearrange V equals D over T. Did I ever tell you what my opinion of the triangle is? You mean that stupid triangle thing? I won't bother telling you what my opinion of that stupid triangle thing is. Bottom line is, sometimes we have to rearrange that equation V equals D over T to solve for D or to solve for T. Our equation says V equals D over T, but we can solve it for D or T by rearranging, by doing some algebra on it. In question 5 and 6, we have to do almost the same thing with a hand rule. We have to rearrange the hand rule. Usually we say, here's which way you stick your thumb, which way do your fingers point? This time we're saying, here's which way I stick my fingers, which way does my thumb point? So we're kind of working it backwards. We know that in this case, it's an electron, so it's going to be a left-hand rule. Fingers are going to go clockwise. My thumb must automatically stick or point out of the page. Now for you guys, again, it's horizontal, so it would point still out of the page, just be towards the ceiling as opposed to towards the back wall. Alpha particle, right-hand rule. Fingers, right fingers, clockwise. Thumb must automatically point into the page. So hand rule algebra. Usually it's thumb, which way do my fingers point? These two questions, it's fingers, which way does my thumb point?